Alright class, despite the lack of 99% of the students today, we're going to be learning about the conservation of momentum using the scientific method. Our first part of the scientific method today is our question. Now our question will be, how does the conservation of momentum affect velocity? Tabitha?
What is the conservation of momentum?
Well, Tabitha, the conservation of momentum states the total linear momentum of a system of particles not acted upon by an external force is constant in magnitude and duration, irrespective of any reactions among the parts of the system. Yes, Allie?
Can you translate that to English, please?
Sure. Well, Allie, simply explain the initial momentum will be equivalent to the final momentum of the system. So now that you have a decent understanding of what the conservation of momentum is, we really need to get you a good grip on what momentum is. So momentum can be defined as mass in motion. If a certain mass has velocity, then it has momentum. And the formula for momentum is P equals M times V. As we know, M equals mass, V is for velocity, and P is your momentum. And don't forget that momentum and velocity are both scalar quantities. So this is on a one-dimensional axis, hence the conservation of momentum has a negative sign, which we will see in the experiment to come. So let's hypothesize about what would happen in an experiment if we had two people separated by 0.6 meters and they were to throw a 15-pound ball at one another. Well, we can hypothesize from the conservation of momentum and from this formula that the thrower of the ball will have to move in the opposite direction so as to fill in the conservation of momentum, or to have that be true, because the ball is going to be moving away from him with a certain momentum, and that has to cancel out or counteract, so they will have to move in the opposite direction. So let's see if it works. Class, I'm going to explain what's going on in this experiment so as to not confuse you in the next step of the scientific method, where I'm going to show our observations and the math behind why this works out. So to start, we have LeBron here, who is going to be sitting on the penny board, very light, and then we have Allie, who's going to be sitting on the very heavy but very nice Miss Roniker's chair. So Caleb is holding the ball initially, and he has no momentum at all, no velocity, just no momentum. So when he throws the ball at Allie, in that exact second, he's going to be moving backwards while the ball moves forward. And this is showing the conservation of momentum, because when he throws that ball, he has no other direction to go besides the opposite, because these two initial and final momentums need to cancel out in this isolated system. So when he throws it, he's going to start to move backwards. But what you may ask is, why doesn't Allie move as far? And the answer to that is, when she catches the ball, she has much more friction on her 6 or 8 wheels compared to the 4 here, and much more mass between the heavier chair than the penny board. And now she is holding the 15-pound or 6.8 kilogram ball, which is also going to slow her velocity down. So when she catches this, she's not going to move near as far as LeBron here. Surprise, looks like, well, we have a board full of math, and that didn't get there magically, but we can pretend it did. So, alright class, now that you've seen the experiment, it is observe and record time. So this is all the data we've got, and I'm going to go through it with you guys. This is Allie in the chair. This is her momentum, is 86.2 kilograms multiplied by 0.09 meters per second. Her mass times her velocity equals 7.76 kilograms times meters per second. There is no name for it, that is just the units for momentum. And then we have the momentum of the ball is equivalent to 6.8 kilograms multiplied by 0.6 meters per second equals 4.08 kilograms times meters per second. And lastly, The student you saw throwing the ball, his name is LeBron. He's actually a foreign exchange student. Darn it, it's LeBron. That's how you pronounce his name. His momentum is 60.5 kilograms multiplied by 0.196 meters per second, which is equivalent to 11.9 kilograms multiplied by meters per second. Now, these two numbers are almost exactly the same, and our formula for the conservation of momentum comes into play with the negative sign. So technically, this would be the negative number right here because it's going in the left direction while LeBron moves in the right. So those equate almost exactly, which is really nice. And as you can see on the board, I used 3 sig figs, and the video we took to get the velocity and the mass, I just measured in pounds and converted it to kilograms. So this is a great example of the conservation of momentum because these are exactly or almost exactly the same. It really shows how these are equivalent, even though that we threw a ball and another person caught it. And it would have been almost exactly the same if it wasn't for Allie's multiple wheels on our chair, which caused extra friction, which affected how much you get or how much energy or how much momentum is taken away from the friction because the velocity changes. So the last part, class, that we need to do is to share this awesome project, and how conservation momentum is a really fun thing to show, and how you can throw something at your friends and watch them move, and there you go, you have an example of the conservation of momentum.